In exercise 1512, you're given a series of molecules here at the top, and you want to match each of those with a spectrum that they give, and they're going to give us a whole bunch of these. So let's look at these spectra, one spectrum at a time, and we'll identify what all the peaks mean, what all the shadows in these dips are being caused by. Once we have that, we'll be able to look back and assign it to one of these molecules. Okay, so for this first one, now anytime you get a new IR spectrum, you draw that vertical line at 1500. And anything to the right of that line is going to be a shadow that's cast by a single bond. So all those are shadows cast by single bonds. Now, another useful line to draw is one at 3000. Because just to the right of 3000, you have that very common landmark, the absorption for an alkane. Now, alkanes, technically, this is just to the right? And this is a carbon, sp3 hybridized carbon to hydrogen bond there. And there are a lot of those in a molecule. Anytime you have even a small molecule like propane, you'd have all of these bonds to hydrogen. And sp3 just means that the carbon has only single bonds. So all of these bonds here in the blue highlight, all of those bonds would absorb in this, just to the right of 3000 wave numbers. So you get a lot of those, and that's partly why there are all these spikes here, mini spikes, but they all kind of merge into one thing. Okay, we have another dip, and this dip is just to the left, this dip here. In fact, that dip, if you follow it down, it's at around 3100. 3100 is a sign that you have an alkene. This is a bond between a carbon that's sp2 hybridized and hydrogen. So this carbon is involved in some sort of a double bond, whereas this other carbon has all single bonds. But it's this bond right here between the carbon and the hydrogen that's casting the shadow. Now you might notice there is another dip here, there's another shadow. That is not one of the ones you'd be expected to know. It's at around 1650, maybe 1600, and that's not represented anywhere here, so you wouldn't have to know that for a test. It happens to be the shadow that's cast by the double bond between the carbons, between two carbons. So all we have evidence for here is a carbon with double bonds, an alkene. So which of these have a double bond between carbons? Well, not that one, that has only single bonds. Not this one, this has an alcohol, so it would have that smooth shadow between 3600 and 3200. Not this, this has carboxylic acids that have that gigantic smooth shadow and a sharp one at 17. Not this, this has the amine, so it would have that, and this is a primary amine, it's only bonded to one carbon, so it would have that sort of shallow absorption with the two bumps at the end, one for each of the hydrogens, between 3300 and 3500. And this is an ester at the far right, so that would have an absorption around 1715, it'd be a sharp one that would go down. So we don't have any of those. What we do have is evidence for this double bond right there. And so this is representing this molecule. That would be the IR spectra. We would match to that molecule. So you'd put maybe A there. Okay, next. Let's move that up so we can see this next one. So here, let's just analyze this, go peak by peak, and then once we know everything we have, we can compare it to the molecules that they give us. So we draw that line at 1500. Every time you see a new IR spectrum, everything to the right of that is the fingerprint region. It's representing all of the single bonds, the shadows cast by all the single bonds in the molecule. There's so many of them, they overlap, mush together. They form that unique region that's hard for a human being to disentangle and interpret. And another place it's useful to draw a line is at around 3000, because you get that very common absorption just to the right of 3000. That is the, just to the right of 3000, whoa. Just to the right of 3000, that's the absorption for an alkane. Excuse me, so you get just to the right of 3000, you get that absorption for an sp3 hybridized carbon, that's a carbon with all single bonds, to a hydrogen. It's this bond here that's casting this shadow. All right, and we have one more absorption. It's this sharp one right here. That sharp one, which is around, let's see, 15, 16, 1700. 1700, and so that is evidence for a ketone. It says 1720. Remember, these are rules of thumb. The things will change a little bit, and also it does look a little bit higher than 1700 itself. So that is being the shadow cast by a carbon to oxygen double bond. So based on this IR spectrum, what it looks like, what we have evidence for, is a ketone. So we can go back up here. Where do we see a ketone? We see it right here. Now technically that is an ester. Esters absorb at a very similar frequency, right, 1740. So you might say, wait a second, how do you know whether it's a ketone or an ester? And technically, just given this IR spectrum, you don't have enough information to decide between those two. But if you notice, the choices they give you, there is no ketone. There is only an ester. And so that is the only possible thing it can be, because the other alternative, the ketone, is not here. And so B would be this ester. So I'll draw that. 1, 2, 4, so I'll draw that here. So there we have it. Okay. Next. So we'll go through this spectrum, we'll identify all the peaks, and then we'll compare them with the molecules they give us. Now a new IR spectrum means a new opportunity to draw a line at 1500. Always draw that first. All of the absorptions to the right of that are going to be caused by the single bonds in the molecule, which overlap and mesh together, but are unique to the molecule, so that's the fingerprint region. Another useful line is a line at 3000, because that helps you to distinguish a very common absorption just to the right of 3000, which is for an alkane. It's in a lot of carbon molecules, sp3, carbon to hydrogen. Remember, sp3 carbon is a carbon that has all single bonds. So that's what this bond here is the bond that's casting this shadow. It's when this bond goes from one quantum wave vibrating to the next, the energy that it takes for that bond to do that is the energy that you get at around this area. And so that's why it casts a shadow there. All right. And that's it. Those are the only things we have here. So what it looks like we have here is an alkane. No double bonds, no other functional groups, something with only carbon and hydrogen single bonds. And so that is this right here, pentane. All right, next. So we've got this spectrum here. So let's just analyze it, identify all the peaks, and then we'll compare it to the molecules they have. First, draw that line at 1500. Everything to the right of that line is going to represent the shadows cast by single bonds in that unique fingerprint region. Another useful place to draw lines is at around 3000. Just to the right of 3000, you'll have this shadow right there. That's a shadow being cast by an sp3 carbon with all single bonds, to a hydrogen. It's this bond right there that casts that shadow. We have a third absorption, this absorption right here. That's a smooth, broad absorption that goes from around 3200 to 3600. And so that is an alcohol. Broad, smooth dip between 3200 and 3600. That's technically the bond between the oxygen and the hydrogen of an alcohol. It goes from one quantum wave vibrating to another when it gets at around that much energy, an energy that corresponds to that many wave numbers. And it's spread out so broadly because of the intermolecular forces that weaken this bond to different amounts in each molecule. So what it looks like we have here is an alcohol. So we can go back and see which of the molecules they gave us was an alcohol, and it looks like it was this one right here. So let's draw that in. We had 5 carbons, and then they have an OH on the end and a methyl group coming up here. So there it is. Okay, next one. New IR spectrum, draw a line at 1500. Everything to the right of that are the shadows being cast by single bonds in this molecule. There are a lot of them. They overlap, mess each other up. That's what you got there. Another useful line is at 3000. If you notice, this starts off pretty smooth and gets a little bumpy to the right of 3000. And that bumpiness is coming from our old friend, the sp3 carbon 2 hydrogen bond. But it's not its normal self here. Normally it's something like that. What we have here is a bigger absorption. This absorption takes up almost a third of the whole spectrum. And that is the shadow cast for the bond between an oxygen and a hydrogen that's involved in a carboxylic acid. So this right here is the spectrum for that carboxylic acid. Now notice it goes from around 2200 to 3600. And so if you go down to this carboxylic acid, you see 2200 and 3600, very broad dip. You also have another one around 1700, and lo and behold, that's here too. So that's the shadow being cast by a carbon to oxygen double bond. Here's 1500 here, go over 1600, 1700. So you can see it's around 1700. So that is that, and then you can put these together and you'll see you have a carbon to oxygen double bond, and then that's going to the oxygen hydrogen, and that's a carboxylic acid. That whole thing. So this molecule is a carboxylic acid. So let's look at what molecules they gave us that have carboxylic acids in them. There is only one, and it is this one right here. So you have those 3 carbons, and a carboxylic acid on either end. Notice, we couldn't get the structure of the exact molecule. We don't know how many carbons you have looking at the IR spectrum. All you know are what functional groups you have, what type of bonds you have. Okay, last but not least, we'll do F. A new IR spectrum, that's a new opportunity to draw a line at 1500 wave numbers. Everything to the right of 1500, all of that, those are shadows being cast by single bonds. They're unique, they interfere with each other, so they're hard to read, but they're unique for each bond, so it's a way to distinguish 2 bonds that have otherwise similar functional groups. So it's called the fingerprint region. Another useful line is at 3000. And you'll notice here we have our characteristic dip just to the right of 3000, our good old friend, the sp3 carbon to hydrogen bond. sp3 carbon, that's just a carbon that has all single bonds. So it's this bond right here that's absorbing that energy there and casting that shadow. Now we have another absorption sort of over here. It doesn't go very far down. And it has two sort of dips at the end. Two dips. Doesn't go very far down. It's around between 3350 and 3500. That is an amine. And because it has two dips between 3350 and 3500, it is a primary amine. Which means you have a nitrogen. Nitrogen tends to form 3 bonds. It has that one lone pair. Primary amines are bonded to 1 carbon. That's what the primary is standing for, the 1 carbon. These other 2 hydrogens, being able to vibrate with each other, are what give rise to the 2 dips. So we have a primary amine. Now we do have yet another shadow being cast, but this is not one of the shadows that are on this table, and so you wouldn't be responsible for identifying that one. You'd only be given a problem where it wasn't necessary to identify that one, and indeed, in this problem here, it's not necessary to identify it. This is another dip the dip here is another dip that would lead you to an amine, to saying that this molecule is representing a primary amine. So we'll go back and we'll see which of the molecules they gave us has a primary amine in it, and it is this last one here. So we've got 4 carbons and then a primary amine at the end. So this nitrogen is only bonded to 1 carbon, so it's a primary amine. And that's in practice with matching IR spectra with different molecules.